Section 6-4 is on the number e. That's that value of 2.718 approximately. Exponential functions and logarithmic differentiation. And the objective here of this section is to use logarithms to differentiate exponential functions. And we'll deal with the idea of logarithmic differentiation actually in the second half of this discussion, but let's deal with some of the properties of exponential and logarithmic functions first. All right. First of all, the number e, again, is that value of approximately 2.718. And it's just a special base that we use for exponential functions, as well as for logarithmic functions, for that matter. But e has this special property for us that the derivative of the exponential function with base e is just itself. Derivative of e to the x is e to the x. That's a very nice derivative. In fact, that's the only derivative we have that's like that, where it's its own derivative. And of course, with that being said, we know that the antiderivative of e to the x dx is also e to the x plus c. So it's a very nice function, even though the number e might not look like a nice number. Turns out to be a nice value for us when we're working with derivatives and antiderivatives. Now, as far as where the value of e comes from, here is the definition of e. It actually involves a limit. This comes about when you start evaluating interest, compounding interest continuously, that you end up with something that involves this value. And that's why your compound interest function, when you're compounding continuously, involves this value of e. It's because of the fact that you're letting n, the number of compoundings, go to infinity. You're actually looking at something that ends up like this second way we've got it written here. But these two are equivalent. E is equal to the limit as n goes to 0 of 1 plus n raised to the 1 over n. And you can see that when you evaluate that, the base of this thing, this part right here, is heading towards a value of 1. It's 1 plus a value, a very small value, so it's heading towards 1. The exponent, on the other hand, up here, 1 divided by 0 is approaching a very, very big number. Again, it's not actually dividing by 0. We're getting closer and closer to 0. So that's going to infinity. So this is taken on the form of 1 raised to the infinite power. And we'll learn later in this chapter that's one of the indeterminate forms for us. We've already seen a couple of them: 0 divided by 0, infinity divided by infinity, and there are several others. This is one of them, 1 raised to the infinite power. So in this form, it's not you can't quite tell why that's the value of e. We got to get a little bit further to understand why that is, but it turns out this is how you can evaluate e. The same thing happens here in the second form, by the way, that if you let n go to infinity, then you have 1 plus 1 over n. And again, 1 over infinity, 1 divided by a really big number, is going to 0. So that's basically the base is heading towards a value of 1. And the exponent up here, of course, is if n is going to infinity, then that exponent is just n, so it's going to infinity. So both of these end up being the same form there. They're indeterminate, so it just turns out these are the same value. They both approach that value of 2.7182. But we will deal with more of those indeterminate forms actually in the next section here of this chapter. All right. I'm going to show you just the graph of, you can graph both of these. I'm going to graph just one though, just to illustrate this, why we get this value. If you take that first form, you could do it with either one, but I'm going to take the first form and work with it. Let me put the graph up here so we can still see the equation. I'm just going to graph in this first form of a limit there, that limit as n goes to 0 of 1 plus n raised to the 1 over n. I'm just going to graph y equals 1 plus x to the 1 over x, just so you can see what happens. So there's our equation. Oops, I got to raise it to that power. I typed that in wrong. Raised to the 1 over x power. And I'm just going to graph this in the standard window. That'll give us an okay graph for what we want to see. The limit that we were working with there is the limit as n goes to 0. So I'm really interested in what's happening as they approach 0. Now this thing is not defined at 0. If you just try to trace it at 0, it's not defined. And you can see that because the exponent is 1 divided by 0. in that case when n is 0, so that's not defined. But instead, well, let's use our table to help us see what's happening as we get closer and closer to that value of x equals 0. So we'll start a table at 0, and we'll just make this a really, really small change in x. And go to your table, and let's just move up here a little bit so we can see both sides of x equals 0. So you can see that to the left of x equals 0, you're at 2.722, 721, 719. And to the right of 0, as we head in towards 0, you get 714, 715, 716. So it's somewhere between 716 and 719. That's that value of E that we're looking at there. You could keep zooming in on this further and further and further and get more and more decimal places of accuracy, but I can definitely tell it's a value of 2.71 something. And it turns out to be this value of E. Okay, you could do the same thing with the second limit there and let x go to infinity. So just plug in bigger and bigger values for x, and you'd see it keeps getting closer and closer to that value of 2.718. In that case, it's a horizontal asymptote for that function because n is going to infinity. All right. So that's the number E, and that's the way it's defined, or the definition of what E is. All right, if you recall back to your studies actually last year in pre-calculus, and you've seen this prior to that as well, a function and its inverse. If you take the composition of a function and its inverse, it turns out that those basically one function undoes the other function. So if I take and plug x into f inverse there, and then take that result and plug it back into function f, I end up getting x out. In other words, you get the same value you plugged in. They undo each other. Whatever f inverse did to x, f undoes all that. It doesn't matter which way you do the composition. So in the second way I've got it written here, I've got f inverse of f of x. Same thing, you get x out of this thing. When I take x and plug it into function f, then f inverse of that value ends up giving me back the value I started with. All right. That works for any function. There's properties that deal with the domain and range of these inverse or of these inside and outside functions that you have to make sure is satisfied. But for the functions we're going to consider here, those things are satisfied. So I'm not going to worry about writing down that detail there for you, but technically there is a little bit more to that. All right, here's the property for exponential and logarithmic functions. Exponential and logarithmic functions, remember, are inverses of each other. And so because of that fact, and that comes straight from the definition of a logarithm, remember the definition of a logarithm tells you can rewrite it as an exponential in an exponential form. Log base y equals log base b of x can be rewritten as b to the y is equal to x. You can rewrite a logarithm as an exponential and vice versa. So turns out that log base e, we found out, is this ln function, the natural log function. In the last section, we proved that. And so the log base e and exponential function with base e, those are inverses of each other. If you have the log base b and a base b exponential, those are inverses. So here we've just let our base be e. So the natural log of e to the x just turns out to be x. And e to the natural log of x just turns out to be x. That's just using this property we just set up above. But if you take the composition of a function and its inverse, turns out that that just gives you the value you're plugging in. In this case, it's x. All right? And we can use that then, that property, along with other properties of logs, to help us simplify problems before we have to find a derivative or an antiderivative, whatever the case may be. So let's take a look at an example here where they're going to give us something like that. This one says to differentiate y equals the cosine of the natural log of e raised to the 7x. Now we have techniques that we could use to evaluate this just as is. But realize that you've got actually 4 functions here that are making up this composition. So that makes a pretty complex derivative there. You've got to use chain rule several times, obviously. Because you've got 7x, and then you're exponentiating that to base c, and then you're taking the log of that, and then the cosine of all that. There's 4 functions there. That means there's going to be 4 links in your chain, 4 derivatives in essence that you've got to find and multiply together with chain rule. We can simplify that, and we can simplify it for this reason, that here I've got the natural log of e to some power. And I just learned that those are inverses of each other, so therefore the composition of those two basically undoes each other, so I can eliminate those. Okay, in essence, I can say I can get rid of this part right here. So this becomes then just the problem of the cosine of 7x. In fact, if you were to graph these two functions, you get the exact same graph. Cosine of 7x is the same as the cosine of the natural log of e to the 7th power. That is only two functions in my composition. I still have to follow chain rule, of course, but I've eliminated two functions that I really didn't need to have to deal with in the problem. So let's take the derivative with chain rule. Derivative of cosine is a negative sign. That's the derivative of the outside. Chain rule says to substitute in the inside function, the 7x, and finally to multiply by the derivative of the inside, which is 7. That's the three steps there, remember, of chain rule. And there is our derivative, negative 7 sine of 7x. All right, you've seen already in the last section, actually, the rule for the change of base of a logarithmic function, that if you have the log base b of x, you can rewrite that as the log base a of x over the log base a of b. You can change the base to any base you want for a logarithm. And you can do the same thing for exponentials. Not something that we do very often, but you can certainly do that. The reason for doing this is if you don't like working with base b exponential functions, base e, we've already started out by saying those are much nicer derivatives and antiderivatives. So you might do a change of base just to simplify the problem. That was the whole reason why we did that, use that property for the composition of inverses on the last example there, to simplify the problem. So here we have b to the x that we're starting off with. And I know that e raised to the natural log of something, those are inverses of each other, this guy right here. These two basically cancel each other out. So in other words, if I were to cancel those out, I have b to the x. So I can rewrite b to the x as e raised to the natural log of b to the x. Now again, the reason for doing that is I've now changed the base of this exponential function from base b to base e. And then not only that, you can see that in that exponent, I've actually got the natural log of b to the x, this part right here. And you've got a property there for logarithms that says if you have the log of a power, you can bring that exponent out front. So that's how we've rewritten it there at the end, is that's the same as e raised to x times the natural log of b, where the exponent now is really a linear function. It's just some constant, natural log of b, times x. That's a linear function. So taking the derivative of that, or the antiderivative, since it's an exponential function, actually becomes a little bit easier to remember, perhaps. It's up to you whether you want to do that or not. We already know the rules for the derivative and antiderivative of a base b exponential function. This just gives you another way to think about that problem. In fact, here to remind you of those properties, here's your rule for the derivative of exponential functions. You have the derivative of b to the x, that it's natural log of the base, natural log of b times b to the x. Or if that's just your base e exponential function, again, because of the fact that the natural log of e is 1, this just turns out to be e to the x. The natural log of e turns out to be 1, so we don't need to write a leading coefficient of 1 there. So the derivatives of exponentials, again, this is the reason for perhaps wanting to do a change of base, because it becomes simpler as far as the derivative and as far as the antiderivative or the integral of exponentials is concerned. So here again, if you want to find the antiderivative of b to the x, it's 1 over the natural log of b times b to the x plus c. And the integral of e to the x, again, we already said that earlier, is e to the x plus c. So you can see it's a little bit simpler. I don't have to worry about that constant of the natural log of b and whether I multiply by it or I divide by it to help me remember the property. All right, if I can convert it over to base c, it might simplify it for you. It's up to you whether you want to remember the properties here for derivatives and antiderivatives for both base b and base e, or use that property for change of base that we just learned and only have to remember base e exponential functions. Either case, you get the same result. One thing that might help you with this, I've tried to give you this hint before, but if you look at or compare this with the power function, if I were to take the derivative of x to the n, my rule is I multiply by some constant, in this case it's the exponent there, n, times x to the n minus 1. It's almost the same function that you started with that you multiply by there. It's x to the n minus 1 instead of x to the n. But notice in both cases here, you multiply by some constant out front. And then times the function in the case of b to the x, or almost the same function in case of a power function. But in both cases, you multiply there. With the antiderivative, if we do the same thing for a power function, x to the nth dx, this becomes 1 over n plus 1 times x to the n plus 1 plus c. And again, in both cases here, you can see that you're dividing or multiplying by the reciprocal, however you want to think of that, out front. And so if you remember that, or that relationship that it has, if you will, to a power function, it might help you remember those properties. All right, let's take a look at one more example. Example number 2 for part A. It says to find the following derivative. Derivative of 8 to the x. All right, now again, you can remember this either way. You can first do a change of base to base e and then take the derivative, or you could just use the rule that we had a second ago for the derivative of base b to the x. I'm just going to use the rule. I think that's the easier way to go, but if you prefer using that change of base thing, then do it. But anyways, the rule here is it's the natural log of the base times your exponential function, 8 to the x. And for part B, this time they ask us to integrate that, the integral of 8 to the x dx. So again, you can either do a change of base to base e, and then integrate that base e exponential function, or use the rule that we already know. I'm going to use that rule. Whichever way you want to do it is up to you, but it's 1 over the natural log of the base times your exponential function, which is 8 to the x plus c. All right, and there's our derivative and our antiderivative for 8 to the x. Obviously, as your exponent there becomes a little more complex, obviously it doesn't have to be just x. It could be x plus 1 or 2x. Things like that will make it a little bit more to deal with in the problem, but you still can find the derivative and antiderivative of that function. All right, and that is the as far as we're going to go here in this first half of this section.